All right, let's do this. We are looking today at a single topic, which is impact, and it is related. 5.4, 15.4. And it is related to what we talked about before, because we talked about, for instance, that ballistic pendulum where the bullet went into impacted, I guess you could say, the piece of wood. And so what we're going to look at now is kind of the behavior of things when they impact. The bullet, though, stuck to the wood, but a lot of times when things bang into each other, they don't stick to each other. They bounce off. And so what we want to think about is like a couple objects bounce into each other, what direction do they go, and how much velocity they have when they do so. Just to kind of set a little bit of background for this, probably the easiest way for you to think about this is kind of just playing pool or something like that. You don't need to know this, but central impact is like a pool ball going in that direction, smacking into another pool ball. So that's just going to stay straight. Does that make sense? If you got a straight in shot, I'm sure you've all played pool at least once. If you got a straight in shot, awesome. You just hit it straight. This ball is going to kind of take off straight. And everything is pretty straightforward. But of course, when it hits at an angle, now things get interesting. So same situation, smack that ball this way, but what if this ball is actually sitting down here so that when this ball gets there, it's kind of like right there. So the question is kind of how's that going to behave? And the interesting thing about it is oblique impact, so hitting at an angle, it creates a coordinate axis when you do that. Interestingly, I'll add this to the pic. Morning, Ian. How you doing? Yeah, Joseph is back. Dude, you gotta send me some emails. I sent you an email. I was like, are you live?
Oh, did you? Oh, did not see it.
Yeah, I just wanted to make sure you were okay or what was going on. Making sure you were coming back. Do you have a sense of where that second ball is gonna go? If it hits, if you will, right there, does it make sense? Two pool balls are only gonna hit kind of at a point. Do you have a sense of what direction that's going to go? Can you define that? Basically, if you drew a center of this ball and a center of that ball, does it make sense? Those 3 points, as mathematicians would say, are collinear, like they're actually going to be lined up. And that kind of creates an axis. I mean, there's a perpendicular axis here to that. And then there's also kind of a parallel axis that goes through all of those. It's not a perfect drawing, so I guess I better throw in a 90 in there since it isn't exactly 90. That's kind of the coordinate axis that happens. It almost doesn't even matter how the other ball got there. But that's the direction that everything is going to kind of travel in now. And one of the things you'll find confusing in this language, I guess, is that this axis X right here and this axis Y. And you might think, well, doesn't really matter which one you call X, which one you call Y. That's actually kind of true. But this one is called the line of impact. I might write LOI sometimes for line of impact. But stop and think about it. That kind of makes sense. Like this is kind of language you'll be stuck with a little bit to get these problems right. And you're going to need to draw this in whenever you have kind of a problem to work and so forth. And of course, I mean, pool is an interesting example, billiards, but you can imagine two cars smacking into each other this way. Saturday, interestingly, I went over to my parents' house just to say hi, and they were watching the National Cornhole Championships. Have you ever seen that? You probably all played cornhole, right? A little bit, and for most of us, it's just kind of like grab the bag, huck it down in the general direction. If you get it to land on the board, you're doing pretty good. If you get one in out of 4 bags and stuff, you're doing pretty good. But these dudes basically can make every shot. So they try to land the first one like in the front. They try to land it in front of the hole to kind of screw it up for the other people because it's actually still fairly hard to swish it. But the reason I bring it up is they would, I'll probably erase this, but if this is the hole and somebody's bag kind of lands right here rectangularly, the next person is good enough that they would actually have their bag come in, hit this bag, so that bag would go off that way, and then theirs would ricochet into the hole, so they'd actually make it, and kick the other one out of the way so it could never be made. Does that make sense? So if you're playing defense, you would throw your bag to kind of land right here, because then it's really easy to hit it with a second bag, and then they both go in the hole, because you really kind of need all 4 years to go in the hole if you're going to be really good. It's kind of what it comes down to. So what you don't want to do is miss and be this guy over here, because then the next person's going to knock you off. Not only that, but they could actually land it on its side so that it would roll over the top of them without knocking the other bag out of the way, and then just go in the hole all by itself. And I was like, dude, crazy. So, this idea of pool or even cornhole, if you're ridiculously good at it, I suppose, or cars, two cars smashing into each other, and where do they go once they bang into each other? And stuff is impacting, knocking into other things all the time. And so, we talked about the kayaker with respect to momentum, and I forgot the other word. I always want to say impact, but it's not impact. What was the other word? Momentum and impulse. Thank you. And how, the kayaker lands on the water, and the amount of time it takes to absorb that hit kind of determines how much force. But there's also a question of, like, what direction do you bounce away? In the case of water, you're just going to kind of land on the water. But I don't land on rocks, but I'll like jump off stuff and jump off a rock on the side in a kayak a lot. Again, you're smacking into stuff. So it's not just kind of what force. It's also, what direction are you going to go? And so really the key is lining up that line of impact. And of course, if they're two circles banging into each other, like a pool ball would be, this is a lot easier to kind of pull off, right? So anyway, line of impact is, well, that's they impact each other, even though, this ball, if you will, is traveling to the right. Oops, that wasn't what I wanted to do. This ball right here was traveling to the right. That's not a thing, if you will. It's kind of almost irrelevant. The speed it, goes at matters and so forth. But it creates its own coordinate axis based on where those two circles kind of kiss into each other. So it makes sense to call that the line of impact, because that's the line in which they impact each other. It's like a brand new line. It's not the line and the ball was traveling in. Does it make sense the ball could have came from over here and it would be the exact same problem? Wherever they hit, that's the new coordinate axis. Doesn't even matter how they got there. Does it make sense that ball could have came from over here? Same exact thing would have happened. So line of impact is entirely determined once they kind of bang into each other. And of course, the sport of curling is a big part of this too, right? It's the same principle. There's actually a couple problems in your book that are curling problems. And so that's traditionally called the x-axis, which sort of makes sense because that's what happens first. They bang into each other, boom, that's the independent variable. Okay, well now we have an x-axis. Well, what's the y-axis? The y-axis is the plane of contact. Of course, I could abbreviate that POC, I suppose. Now, for me, when I sort of read the first one, line of impact, I thought, okay, great. But then as soon as you say plane of contact, well, now all of a sudden I get them mixed up. I mean, I've taught this 5 or 6 times now, kind of still get them mixed up. It doesn't so much matter what they are called as much as what each of them does. The key thing to this is kind of that's what's going to happen to these two balls in the end. Basically, if this is kind of ball 1, this is the direction that they're actually going to go. In other words, ball 1 is going to be up there, and if this is ball 2 is going to be right there. Like that's where they're going to go. Does that make sense? So that's why those two planes exist. So in the case of pool, for instance, a lot of times you'll knock a ball over into a pocket. Say there's a pocket over here at X, and that's great. But your cue ball will actually bounce off at a different angle, and then that'll like go in a pocket too, and then you scratched or whatever. So that's just an interesting idea. So does it make sense kind of why this exists? And again, I think it's really important just to reiterate that it doesn't make any difference where ball one came from. It's just kind of where do they impact each other. Once that's determined, it determines the coordinate axis. And now we know which direction everything's going to travel. As I said, way more complicated if it's a truck or something, right? Because the truck is going to smash in, it's not round. And so a little more complicated. Make my one look like my other one did. So that's a super important idea. Now let's kind of highlight this, say a little bit more. Actually, I think I'll draw like even a brand new drawing just to kind of, and I'll even kind of make it hit in some totally different orientation or something like that. But let's say this is ball A, and it's going to cruise over here into this location. Where it is waiting to smack into B. So armed with that alone, do you have a sense of where everything is going to go? Do you recognize that this is the plane of, or the line of impact? And so I'll put this over here. That's going to be the line of impact, and that will determine the fact that ball B is going to go in this direction. Now, let's look a little more seriously at this other axis, the plane of contact. Where's that second ball actually going to go? Is it going to follow this line over here? The answer is not really. It's actually like, does it make sense? The center of it's right there. I mean, think of this as if it was a wall. Like pretend there's no other ball there. Pretend if that plane of contact was just a wall. What happens to that ball if it bounces off that wall? Isn't it actually going to go like this way? Does that make sense? That's what's really going to happen. So going back up here to just make you think a little bit deeper, is that ball going to follow that line? No, it's actually going to go more like over here. And notice it's kind of based off the center line. It's the center of the ball. That's really where it's going to go.
So the one that follows a line is B.
Say that one more time.
So the only one that follows
Yeah,
line.
that's exactly right. The line of impact, that's where B is going to go for sure, because it's being impacted. And again, all B knows is it got touched. It got touched right there, which is the reason it's going that direction. So B is following one of those lines. The other one's acting more like a wall. As far as A knows, it just hit a wall. It didn't hit a ball. You understand that? It hit a ball, it hit a wall, but the wall gave a little bit. Does it make sense? It doesn't have to. Like if it was a wall, if I dropped it in the concrete, it's not going to give. And that's kind of what's interesting about this. So this is where A is actually going to go. Now, this is kind of where the XY thing comes in a little bit. If I give those labels and I just call this X and this Y, sticking with the same convention I used before. If this has a velocity A in the Y direction to start with, and notice it has both, it's going in the X and in the Y. But, you know, part of it is going in the Y direction, part of it's going in the X, right? Part of it's going this way in the X direction. Part of it's going this way in the Y direction. It's got both those components because, well, it's coming in obliquely. It's coming in at an angle. But then when it bounces off, it still has a velocity in Y, but what's the difference between the two? If this is the initial and this is the final, and it also has a initial in the X direction and a final in the X direction. The question is, how are those related to each other? I want you to think about it. If I drop a ping pong ball or something like that, and it bounces off this table, which is pretty hard, pretty rigid, right? Does it come back up to the same height?
No.
No. If it did, that would solve the energy crisis, like you'd have perpetual motion. But if it's really springy, if it's like a golf ball or something like that, it'll bounce pretty close. But does it make sense if it's like a hacky sack, like it might barely get off the ground at all? So depending on the ball, depending on the wall, it's going to absorb something in terms of how much it rebounds. So the velocity of AX initial is always going to be bigger than the velocity of AX final. It's not going to bounce back. Let's see, am I saying that right? Yeah, X. So that's the ping pong ball dropping on the table. Does that make sense? So you're going to lose energy. It's not going to bounce off the same. However, surprisingly, or maybe surprisingly, the velocity of A in the Y direction initial does not change at all. So I guess you could say, that's a good question. Did you figure it out? Well, relative to Y, this ball right here is moving in this direction. When it bounces off, it continues to move in that direction. So they are going the same direction, whether you want to call it positive or negative, they'll both be positive or they'll both be negative. They didn't change directions. Now X, it did. It was going right, now it's going to go left. Now, of course, I should be more precise and not say nothing is lost and something is lost. It's something more like, well, velocity is lost, right? Now, is that technically perfect? I mean, if a ball came in this way and it bounced off the table and kept going in this direction, does it kind of get a little friction, like a little skid right there? Probably. Again, it depends on how slippery that surface is. I would say if it's a ping pong ball, which is really slippery and also doesn't weigh very much, when it bounced off, it would probably be immeasurably close. But if it was something rubbery and it hit something, well, like the carpet that isn't as slick, it might skid and kind of not go. So understand, I mean, the book is oversimplifying this concept a little bit. But think of a ping pong ball skidding across the table. Again, ball A does not know that it just hit another ball. It just hit something and it's going to rebound as a result of it. So you got some problems where it hits a wall, which is going to push back a lot harder. Do you agree that a lot is going to be lost in this situation in X because of the fact that the other ball is, able to move? Yeah, that's right. And I actually purposely drew this so that this distance right here was much larger than this, because do you see how it didn't come back to the same exact location? So really with this, maybe you've heard this phrase before in like a physics class, like a ball comes in to hit a wall like this, and whatever this angle is right here, then it bounces back off and goes off in that direction. And physicists say the angle of incidence is equal to the angle of reflection. It's actually not true. That's what we're getting. It's something a little more serious here. Now, is it relatively close? The answer is yes, if not much energy is lost. And a ping pong ball bouncing, which is really lightweight and bouncing off this table, not much is going to get lost. That's a very we'll talk about this in a minute. Let's see, is it plastic or elastic? I can't remember. I'll write this down, but
Perfect environment. It would be
yes, that's exactly right. In sort of a theoretical environment. Plastic, elastic. I'll show you on your note sheet. I'll show you on our note sheet in a second. That's actually not quite true, and it can be really not true. And I guess the thing I want you to understand is that's kind of true if it's a wall and you have a good ball and a really hard wall. That's roughly true. But if it hits a ball where that ball is giving a lot, or even a wall that's made out of something kind of soft, like a trampoline or something of that nature, then this ball's really going to go, well, not quite as high. It's going to be more like that. Does that make sense? Does it make sense that the wall absorbs some of it? And again, if this isn't a wall and that ball actually goes in that direction, it sort of makes sense that it's not going to be able to rebound quite as hard. And so that's what we're kind of talking about here. Basically, you only get some percentage back. That's what you get. Some percent of the velocity in x is lost or retained, however you want to look at it. And we have a name for this. E for the coefficient of restitution, I think is what it's called. Let me pull up the note sheet really quick and let's just look at what I have written down so that you can stare at for your test and so forth. And the only thing that you really need for this section, there it is, my friends, the coefficient of restitution. Restitution is like, somebody stole my money and then they paid me restitution. I got it back again. It's kind of a good word. If you have a kind of a conceptual understanding of what restitution is, you lost something and then you got it back again. So what percent? It's the percent of energy remaining to rebound from a collision. And notice I said in dark, along the line of impact. So if E is 0, then that's considered, you don't need to know this, but that's considered plastic, like it's stuck. It's stuck to it. A hacky sack bouncing off the table is probably not going to bounce at all. It's just going to stick. So that's 0%. You got nothing back, basically. It had all this energy coming in. How much came back? None. What if E was much higher? Elastic. Again, that's like a trampoline. You're getting it all back. Now that's impossible, right? Theoretically, you can say it's close enough if you want to. Angle of incidence equals angle of reflection. But realistically, 99%. I mean, it's a percentage, and it's always going to be less than 1. Now, notice the calculation for it. This is really the only equation that you need in this section right here. So I'm looking at these velocities. In the end, what you're going to get for most of these problems is some kind of you'll be given the coefficient of restitution, just like the coefficient of friction or something like that. And it'll be like, oh yeah, because this is a ping pong ball and a carpet floor, you'll get 80% back. That's what you'll get. Whatever you had going in, you'll get 80% of it back to kind of bounce out. So what do? You take the ball that got hit's velocity minus the ball that hit its velocity for final, and you divide by, well, the initial. So the difference between their relative velocities later minus the velocities earlier. Does it make sense that quantity is going to be less than 1? Isn't this smaller? Isn't the velocity final after something because something was lost? Isn't the final going to be smaller than the bigger, or smaller than the kind of this one, the larger? This is the initial energy, if you will, in the bottom, and the top is kind of the top energy. Well, you're not going to quite get as much out, maybe 80%. So it kind of makes sense where that formula comes from a little bit, doesn't it? And really the negative sign, if you will, you might notice it's like, oh yeah, B came first up here, but then A came first down there. That's just going to make sure it comes out as a positive number. So it's kind of the relative difference of speeds. How much speed did you have relative to each other? And again, this is kind of a neat thought, but it's like, am I moving toward this podium right now? The sort of obvious answer is yes. But if the Earth is spinning, I might be walking in such a fashion that I'm standing still, and then that's moving on the Earth, if you will. I mean, that frame of motion business that you talk about in physics. So it actually doesn't matter most of the time, ball B, if you will, is going to be just sitting there, and then the other one comes up and slams into it, so forth. But anyway, I just want you to have a little sense of conceptual understanding of that. I'm just trying to figure out the relative speed between the two of them. What was it initially? What is it later? Well, whatever that difference is, whatever that division is, gives me a percentage. Well, let's try a problem. Let's see, let's do 87 first. Because this is similar to what we've just been looking at. And you might recognize this is the sport of curling. And it's pretty accurate. And so here comes this ball A, or stone as they call them in this sport. So here it comes ripping in. Notice they're calling it velocity A1, not A initial, which is fine, whatever. So it's coming in 8 feet per second, bam, hits it. So now there's an X and Y axis. Do you see that? Again, they use the convention that I was showing you. The line connecting the centers of those two round objects is kind of the X axis. And we call that the line of impact, if I remember right. And so the important part of this is that's the direction that B is actually going to go. We know that kind of for sure. B is going to go that way. But A thinks it hit a wall just now, and B gave a lot, so the coefficient of restitution is going to be a smaller percentage. It's not going to be 99% here. It's going to be something less, 80%, 70%, something like that. So A is going to bounce off, and notice I'm drawing this from the center, kind of in this direction. And notice I purposely drew, it looks to me like at a glance, this angle, I'm going to erase this, but that might be 70 degrees, whereas this over here is only 30, like angle of incidence is not equal to angle of reflection here. It's going to bounce off over there somewhere. So I just have a speed going in, and I just kind of want to figure the things I'd like to know is basically where's B going to go? How fast is B going to be going? Where's A going to go? And how fast is it going to be going? It would be cool if you could figure that out. And that seems kind of neat, logical, cool. If it's a game and I could control that, know that, that'd be kind of awesome. But again, I mean, isn't this a crazy oversimplification? Like it has to be round. we can't do this. It's gonna be really complicated if it's some car or some other kind of a shape. So let's see, I got some dimensions on there. I'm just kind of staring at the figure, make sure I understand it. So Y is the wall. And again, that's kind of why it's cool that it's called the plane of contact, because A doesn't know that it's a ball. It's not a ball of contact, it's a plane. It thinks it hit a wall. So you might, I don't know, to try to keep them straight for whatever reason. Line of impact, yeah, that's the line in which those two run into each other. And oh yeah, A thinks it hit a plane. And so, okay, great. I got some dimensions there. I'm looking at 3 feet thinking, why do I need to know that? I see that it came in at a 30-degree angle. That's kind of telling me what angle it hit it at. I can tell that's important. If I didn't know that, I wouldn't be able to make any progress with this. And then 8 feet per second. Okay, cool. So what do they tell me? They say blah, 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 blah. Strike each other. Each stone is smooth. Again, that's code for nothing is lost. There's no friction loss. And that's what I said before. That's their way of telling you the velocity in the Y direction didn't change. If they're not smooth, if there was friction, then the velocity in Y would change. Let's see, important things. They have a weight of 47 pounds. I'm thinking to myself, you know, does the weight matter? It kind of seems like it would, especially if one was really light. Does it make sense if a ping pong ball came in and hit a curling stone? The curling stone, the one it hit, probably wouldn't even move. If A was a ping pong ball, that would matter. The relative weights do seem like they would matter. And isn't that kind of what momentum was about before? Momentum was velocity and mass kind of rolled together. Notice they tell us that coefficient of restitution is 80%, 0.8. And they tell us B was just sitting there when it got hit. We don't have to worry about friction. And so, okay, what happens to their speed? So basically I have 8 feet per second of, I don't know, energy, quote, coming in. and it's going to get transferred to B. And so some of that 8's going to B and some of that 8's staying with A. And so cool. I wonder if we can figure out what's happening in this situation. And I'm going to stick with, if I need to know this, actually I don't know, but you know, they label it X and Y. So I'm just going to call that positive X and positive Y. That's what kind of we did before. So I'll call those the positive directions. Because the direction something is traveling does matter. And let's see, of course I see this. That's not what I wanted. I see this kind of right triangle here. So what I need to do is convert that 8 feet per second into the coordinate system, like we've done before. Because it's not acting in the coordinate system, I'm a little confused. Remember, the 8 is going to have to be the hypotenuse. Notice, and I don't think this is obvious, but notice I didn't draw the right triangle this way, where that was 90 degrees, because then the 8 would not have been the largest of the vector velocities there. 8's got to be the largest. So I drew the right triangle in this way. So let's see. Let's just figure out. I don't even know if I need to know this, but it just seems like something I should figure out. So let's see. The velocity in A in the X direction. X would be along this axis. That's the cosine of 30. So that'd be 8 times the cosine of 30, would it not? Do you agree with that? And again, I might even say initial, because it's not going to have the same X velocity after it bounces off. And based on my coordinate direction, it's actually going away from positive X, so it's actually negative. So I punch that in, I get negative 6.928. So I don't care, like the way the book labeled it is great. Velocity of A1, velocity of A2, A1X, whatever. I just like initial and final for some reason. And let's see, similarly then, the velocity of A in the Y direction initial would be, well, notice it is actually going to the right. This would be it right here, going to the right. So that is in the positive direction of Y, but that's the opposite of 30, so that'd be sine. So that'd be 8 sine of 30. And it would actually be positive, which is actually exactly 4. Sine of 30 happens to be a half, so it's exactly 4 feet per second. So, okay, I've converted that 8 into the coordinate system now. And the important thing to understand is in the Y direction, it's not going to change. 4, it's going to stay 4. However, 6.928 is going to get smaller. It's not going to bounce back toward us with that same bounce off the wall. And it's that E that I'm going to need to kind of figure that out. Now, I said before that, you know, because there's no force, I mean, there's no friction loss here and so forth. And we understand kind of just vaguely based on the concept of momentum that 47 pounds, those are huge. I mean, some of you guys lift weights, that's a 45. I mean, those are heavy. They got a lot of inertia to them and so forth. So that seems like it'd have to figure in. And that's exactly true. The conservation of momentum is the way to kind of get this thing rolling. So put simply, that was the sum of all of the initial momentums. Momentum was mass times velocity. The sum of their momentums at the start will equal the sum of their momentums later on. And notice their mass isn't going to change in this case. An explosion didn't happen, so the mass doesn't need to be called initial and final, but their velocity does. And they each have initial velocity, initial momentums. Oh, well, I guess B doesn't because it doesn't have a velocity, right? But they'll both have velocities afterwards. And so does the logic of why that kind of fits in this situation make sense to you? So let's see, what do we got then? And again, notice I've converted it to the kind of correct coordinate axis. So I'm going to do this particularly for X. Now, why am I doing this for X? I'll let you think about that for just a second. But do you agree that 47 over 32.2, remember mass is not the same as force. So unfortunately, because this is in our system, I got to divide by the acceleration of gravity. 47 divided by the acceleration of gravity would become a mass. And I have that initial one in the X direction. We just said coming in at negative 6.928. So that's how much momentum A is coming in at, right? And then I also have the other one that has some momentum, but it doesn't because it doesn't have any velocity. So I could have left that off. So one had all the momentum, and now on the other side, they both have some. It's been transferred. How much does the A stone have? Well, we don't know. That's the velocity in the language I was using of A in the X direction final. I don't know what that velocity is. It bounces off at some other velocity. I don't know what it is.
Speed right on X.
This velocity of A in the X direction?
No, the B. The next thing you're doing. For B, since it just goes straight on the X direction. And its momentum is
That's a good question. What do y'all think? So my gut reaction is just to kind of write it down and say, okay, well then you got a certain BX final. But what's zero about it is Y. It's not going in the Y direction. It's going in X. So it's got an X velocity. It just doesn't have a Y velocity, the B ball. Do you agree with that? I mean, isn't it going this way? Therefore, it's not going anywhere in Y. Its final velocity in Y is zero, but not X. X, it's actually going in X. And notice it's going negatively since we called this positive. So it's going that way. It's going to go negative X. A is going to go this direction. Notice that's positive. So the X direction for A is actually going to be positive, but it won't be as big as it used to be because it lost something. What would it look like if I did this in Y? Yeah. See, if we did this in Y, we already said that in Y, this is just going to stay 4. So there's no reason to do it. And in Y, this one's going to be 0. So it's like we already know what's happening in Y. We don't need to write Y out. The velocity of the A ball in Y was 4, and it will be 4 later. The B ball, and that's why you set this axis the way you do, the B ball isn't moving in Y, so it has nothing. So we don't really need to do this with Y. We only need to do this with X. Now, do I like this equation algebraically? I do not, because it's got 2 unknowns in it. And in a sense, you know, my gut reaction to that is to stare at this and say, well, yeah, I didn't know I know what direction they're going to go. Well, that's not true. I don't even know what direction they're going to go. I know where B is going to go, but I don't know where A is going to go. But I didn't know what the speeds were. And look, I wrote an equation that doesn't help because I still don't know what they are. Well, this is where the coefficient of restitution equation comes in, though, because that's going to be our second equation with 2 unknowns. So the fact that we knew we're going to get 80% of whatever happened in X back. Now, is that as simple as just saying, oh, well, then take 80% of 6.928? Let that hang for just a minute. Think about that. Is it as simple as just saying, sweet, 80% of that?
You could rewrite the impact equation, and you'll have two unknown variables, and you have that as all of those are the extra.
Yeah, the safest thing is to, go ahead and use the equation. We were told that E, and be looking at your note sheet, I'll flip back and forth a little bit. We're told that E is 0.8, but that it was equal to the velocity of the B ball in the X direction final minus the velocity of the A ball in the X direction final divided by, is this right? The velocity of the A ball in the Y direction initial backwards. I wrote it wrong, didn't I?
It's just final and initial.
Actually, I gotta look at the note sheet because I'm totally screwing it up.
It's just says final and initial.
Yeah, it doesn't say
either
right.
one.
Yeah, it doesn't say. Now, which one are we doing? We're doing X because we already know about Y. So we're interested in X. Does that make sense?
Yeah.
But
But we couldn't do X over Y.
That's right. You can't do X over Y. It's just all X's. So,
But is the 0.8 overall, or can it also be directional? Overall.
well, the cool thing is these velocities are going to give us direction. That's what's kind of neat about it. I'll show you that in a minute. So yeah, everything here pertains to the thing that's changing. So E, the coefficient of restitution, is only talking about in the X direction. Does that make sense? It's not Y because nothing is lost in Y. So all of these are X's. So you have velocity of A of X initial minus velocity of B of X initial. It's all X's. And, I've taught this class a lot of times, but now that I think about it, doesn't it seem like that'd be nice if it was on the note sheet, like put X's on there, right? I think I should do that. And so, do I know any of those? Well, I know the A ball's initial speed, don't I? Wasn't that in the X direction, negative 6.982? That was its initial speed. What was the B ball's initial velocity?
0.
Nada, it wasn't moving at all. What about those two on the top? They're both unknown, but now I have two equations, two unknowns. You see what I'm saying? So that's the beauty of that coefficient of restitution equation. So thanks to the conservation of momentum as a physics principle and this coefficient of restitution equation, I can solve this system. Again, solve this any way that you want to. I don't care. I'm just looking at my notes because I was just going to write it down, but I have written down this answer, but I'm kind of looking at it, kind of not trusting it. Let's just stare at that for a second. So, because I did this 2 years ago, I'm just kind of staring at my note sheet. Does that make sense? Is that what X would do? Does that make sense? The A ball. I want you to think really carefully about this. What does that mean? What does that mean about my drawing up there, if that's true? Notice it's negative. It's not very big and it's negative. What does it mean if it's negative?
Is it negative to the direction of travel or the planar?
Remember this right here was positive direction, and didn't this bounce off in the positive direction? So either it should have came out positive and did something wrong, or is it possible that it actually is still going? Is it possible it's actually still going in that direction? Like it hit it and then kept on going? It is, and that's, so I did not do this wrong. In the end, it's like, that's not what happened here, which is kind of cool, isn't it? So it had enough momentum that it didn't bounce off that wall, if you will. Can you appreciate if A was much lighter, it probably would have went where I initially said, but it's heavy enough and it had all the momentum to start with. And although it lost some of it, it's not going as fast as it was before. And notice it lost a lot of it, because wasn't it going 6.9 in the X direction? And notice it lost almost all of that, but it was still going negatively. So that's kind of cool to understand.
Question.
Go ahead.
Just to clarify, travel direction does not imply that it's the positive side. Because I keep going to the whole thing with where we're doing row and all that, where the travel is giving us positive.
Which velocity you're talking about when you say that?
No, just the direction as the thing is going. That doesn't mean that anything, how it's going straight up, that means up is positive and down is negative.
Well, that's up to you. I decided, I mean, first of all, up and down don't make any difference here. We had to convert it to what we're calling X and Y.
What I'm saying, because you got a negative on the velocity, so I'm assuming that because its direction was towards the left and it bounced off to the right, it would be negative. Because if it's traveling to the left, that means everything to the left is positive and everything to the right is negative.
Well, the entire thing hangs only on this brand new axis that we have. As soon as I converted, like eight was nowhere. I mean, I could have made a normal XY axis that's horizontal and vertical, but because of the way these hit each other, it was way better to take that 8 in the orientation it was to the brand new axis, the brand new weird angled oblique axis, and convert it. As soon as I did that, 8 really doesn't exist anymore. And because I chose X to be positive and Y to be positive in the way that I did, and I didn't have to, like you could have said, well, you know, that X is like down, and so that feels more like negative. Great, it's not going to change anything. Relative to what I called positive, you know, I got these positive and negative answers. If you switch that, then our answers would still look the same. Now, of course, you probably understand B definitely has to go the way that I drew it, and that is X negative. So the fact that it comes out negative isn't a surprise. Interestingly, notice it got most of the speed. It got almost all of it. Isn't that kind of strange? Do you have any experience with playing pool where the balls are fairly heavy? That's actually true, isn't it? The new ball gets all of it. Have you seen that? I don't even know what that thing's called, but you have those 5 or 6 steel balls hanging from strings and they kind of you do this kind of thing. I forgot what that thing's called, but that's kind of what's going on there. It smacks into them and then it kind of stops. And then the one on the other side goes and shoots out. Well, that's what's happening here, isn't it? Most of that energy actually went into the other ball.
I used to play this game, pool game on my phone. It's called 8 Ball.
Yep.
When it literally shows the axis. Like.
Oh, yeah.
So it
Mhm.
literally-
Yeah, you like pull it back
Now,
to, and then you go let go or something and it goes pop and
And it
hits it.
kind of shows the velocities too, because depending on the angle, one of the lines would be longer.
Mm-hmm.
Saying like, oh, it's gonna go faster this direction.
Yeah, it gave you kind of a vector as to what direction it would go and a length to kind of send you in that direction. Yeah.
Yeah. I think you just drastically improved the pool game.
Yeah, so I mean, oddly, I'll draw this over here on the board, but if like this is the pool table and you're trying to go into that pocket and you have this ball over here, and your cue ball's out here and you're like, okay, I know I have to hit that on the left and get it to go in that pocket. Really what you're doing is you're trying to hit this ball so it makes contact right there. But the problem is it's not the center of it. Does that make sense? You got to get this ball to kiss that ball right there. So what you really need is the ball to be right there, and it's there that you actually need to shoot. You don't aim at that spot, you aim at that spot. You see what I'm saying? Now, if you get good at pool, you just kind of feel that, you don't think about it, but you literally could lay a string line out and, you know, take another ball and kind of set it there and make a mark where the center is, and then just aim your ball at that mark that actually isn't at the ball. And you're exactly right. Like, this should actually make the pool game better. So that's kind of cool. Let's see, have we answered the question? Is that what it asked? To determine their speeds just after collision. Initially, A has. The answer is yes, in the X direction. But what about the Y direction?
Oh, there isn't. Travel in the right direction. Only follow the x-axis.
The velocity of B is not in the Y direction at all. That's exactly right. It went straight along that line of impact, so it has no velocity at all. But what about the velocity of A final? Well, we said earlier that the velocity of A final is exactly the same as the velocity of A initial. And since initially it was 4, it's still 4. So notice B, we actually know exactly where it's going. It's going 6.24 along the x-axis. But notice A is not going negative 0.69. It's going negative 0.69 in the X direction, but it's also going 4 in the Y direction. So let's actually stop to think about, like, what does that actually mean then?
We have to get it back to one single one, so take the magnitude of it.
Yeah, that's exactly right. So if you just want to know what the velocity of A final is, you'd have to take the square root of those two added together. Which is approximately 4.06. I would assume that's probably what's in the back of the book here. So this is probably what you'd see in the back of the book. And, you know, down here, I mean, I guess it's kind of good to leave the X in that, right? I was about to take the X out and just say that's the final, but at least, but this is also telling you, yeah, it's following in that direction. Or you could take the X out and say along the line of impact or something like that. So maybe this is interesting. Let's think about this just because it might be fun. Our axis looked something like this. And so we're saying the A ball was basically going for this direction, correct? Because we said that was positive Y and it came out positive 4. But then this was positive X. I wrote Y. This was positive X, and we said it was actually going, nope, not that direction, but this direction, 0.69, right? And so this is actually the kind of the vector answer for the velocity of A final, like it's actually going that direction. So we actually do know what direction it's going. And if we wanted to, I think we could say tangent of theta equals opposite. Notice I took the negative sign out because my picture shows what's negative. That's up to you. And if I do that, I get that theta is approximately 10 degrees. So it's like, oh, that's actually rad. So not only do I know how fast they're going, I even kind of know what direction they're going thanks to those two calculations. So with respect to pool up here, bam, I hit that ball and it went in the pocket, which is rad. That's kind of cool. But it's like, where does this ball go now? I can actually figure out how fast it's going to go, where it's going to go. You can imagine theoretically, if you had some sense of how friction worked, it's like it has enough velocity, it's going to go over here, funk, and then stop right there, because of how much velocity it had. Of course, it's friction bringing it to a stop, so you'd have to get serious about friction to figure that out, right? If you played much pool, you know that it's not about just making that shot, but setting yourself up for the next one. And so, how hard do I hit that so that, because it doesn't matter how hard I hit this, that ball is going to go in that pocket. I mean, if I hit it too hard, it can bounce out. If I hit it too soft, it won't make it there, but you got a lot of range in there. And if I hammer this really hard, then it's going to go maybe this way, bounce here, and go way down at the other end and set me up for this next shot over here. If I hit it nice and soft, then it'll just kind of die right there, and it sets me up for that shot. And of course, it's even worse in the sense that you can hit this ball with some English on it, hit it left, hit it right. And when it hits this wall, it'll spin and bounce off at some weird angle. And, I played a lot of pool. I love that game. So, if you get really good, you can run the table like the other guys and get a turn. I haven't done that too many times, but I've done it. So I hope that you look at this and think, that's really cool. I mean, that you can actually understand everything here. Now, one of the things that might bother you a little bit is, where did that 0.8 come from? Notice every part of this was doable, except for 0.8 just kind of dropped out of the sky. Is there some way you could get that? And we are going to do a project about this here really quick. But the answer is yeah. Like if I dropped the ball I was doing this with, like a golf ball, on the table and it bounced and came back up, we could take some measurements there, even rough, just with a cell phone and a tape measure behind it, something kind of cheesy. And you could actually come up with a decent value for that. The gist of this project is going to be something like, if I put this table here and I drop the ball right here and it hits this, could I figure out, given the fact that it's impacting more than another ball to the table this time, I know it's going to hit here and then kind of spring off that direction. And once it leaves here, does it make sense it's now a projectile, which we've played with some more? So the question is, could I bounce the ball on this and figure out E? And then based on height, could I know how fast it was going when it got here, just based on physics? Do I have to have a radar gun to know how fast it's going? No, I just drop it from its definable height. I should know how fast it's going. I should be able to lay my phone on this and know what angle it's at. And I should actually be able to figure out where it's going to land, like over there on the floor somewhere, at least reasonably, even with crappy tools. All right.
Well, it's the AT plus initial velocity. Initial velocity is 0, so it's just acceleration times time. Or the distance. Yeah.
So I think it would make sense then if we did one more question, kind of related to this, related to what I just discussed with respect to a project, but also that you would just see that this is the same problem. Same in the sense that a ball is going to bounce off something. It's just not going to bounce off of a ball this time. It's going to bounce off of a wall. Now, I want you to think about one thing before this. We kind of have the XY axis projectile motion option for this problem, where we said, oh yeah, whatever its X velocity is, it's going to stay that way as it flies through the air. But Y has an acceleration of gravity that's pulling it down. And so we can use all of our position, acceleration, and velocity equations clear back at the start of this class. We also have now the conservation of energy option. And what we learned roughly was the second of those two is much easier. whatever energy it had initially. Notice it's got some initial energy based on the fact that it's 2 meters off the ground. It's got some potential energy. So it's got energy because of that, but then it's also shot at 6 meters a second. So it's got some initial energy to it. But the difference this time is we're going to kind of treat, this like there's ball B. Does that make sense? Except for we just don't care where ball B goes because it's not a ball. It's not actually going anywhere, right? But as far as ball A is concerned, does it make sense? It doesn't know. It doesn't know what it just hit. It's just going to get more restitution, I guess you will, this time. But that's what's kind of cool. This is actually the same problem. So let's take door number 2. So let's see, what do I know? Okay, I know how much its mass is. Notice it's a mass. So this is a metric problem. 6 meters a second. Okay, cool. Restitution between the ball and the surface. They're saying that's the same. Notice before I said that would be more. It would be more unless it's a different ball. Does that make sense? If the wall was soft, if it landed on a high jump mat, which has got an absorbing capacity to it. I mean, it would be more if it was like a normal concrete floor and that was a ping pong ball or something like that. But it could be less, actually. It could be 50%. So whatever, who cares? Just some number. And so, as we said, it's not going to bounce as high as it was before. And the picture is drawn accurately in that regard, since 80% of its direction is going to be taken up. And so let's see, well, where's the line of impact? Where's where is all this stuff? Remember, as I said before, it's kind of like this ball is here and the wall is there. So that's what we're calling the x-axis. And because that's vertical, I'm gonna put that up there. Now, again, that bugs me, right? Because I'm used to thinking of that as y. So the fact that it happens to be vertical is just unfortunate, I guess you could say. The only reason to keep x and y separate like this carefully is just to remember that x is the velocity that's going to change, but y is not. Whatever its y velocity is, it's going to stay the same, but its x velocity is going to change. So in a sense, in this problem, it's sort of unfortunate that this lines up with vertical and horizontal, because now I'm confused because I'm wanting to call that y. I'll call that positive y.
Why?
Hmm.
Wait, why are you calling that one?
Only because that's the one that stays constant. Whatever its y velocity is, it's going to stay the same. So I'm using the convention that the plane of contact that it's going to bounce off of was called the y-axis, and that the velocity of y, whatever it is not going to change. Whereas the velocity in x, the line of impact. Again, what's confusing about that is like plane of impact, line of contact, like you could totally get the language all confused. Okay, so work and energy is unchanged. So I don't know if I need to know this, but I'm kind of just curious. If I kind of took it to that top location up there. So let's see, I've got A, B, and C. I guess I'll call that point D. So I'm going to use energy equations, work and energy. And specifically, I'm just going to do it from A to D. I don't know if I need to know that. Let's let that hang and think about that. I just kind of I think it's interesting because whatever height that is, I'm assuming, and it's going to be higher than 2 based on the picture, that the final height y down there also to the center is, going to be less than that. So I'm just curious. Maybe I should just go straight from A to B, right? I'm going to rewrite B down here since I screwed it all up. Maybe I should just go straight from A to B. Maybe I don't need to do this, but let's just play with it anyway. Okay, so let's see. Work and energy equations. 1/2 times the mass times the velocity squared. That was the energy that was kinetic motion energy. And then we had work, which was a force times a distance. That was the potential energy. And we said, yeah, whatever that is at the start, that's going to be what it is later on. Okay. So let's play with that just a little bit. I won't bother to write initial and final and all that kind of stuff in there, but notice I don't have two balls to worry about. This is really just A. Okay, so I got mass of the ball A. Yeah, I know that. That's just 0.5. And notice it's in kilograms. That's good because force is kilogram meters per second squared. So that's good. I'll just leave that off. And it's got a velocity. Let's see. Do I have to change this? Do I have to change this to X? Do I get to just say 6 here? Or does it actually, do I have to kind of do what I did before and make this kind of X and Y related? I don't think that's obvious. And the answer is because the velocity in Y is going to stay unchanged and the velocity in X is going to change. I do need to do that. So maybe you notice in this picture that in the X direction, this would be the X direction right there. The opposite of 30, that'd be sine. So if I modify this with the sine of 30, I'll go up here and kind of add this note in X. I'm doing this in the X direction because I don't care about Y. Y is easy. I already know the answer to Y. So that's its initial kinetic energy. What about its initial kind of work energy, force times distance? Well, I've got a force, 0.5 kilograms, but I've got to multiply that by 9.81 meters per second squared to make it a force. Mass times acceleration is force. Force equals mass times acceleration. Let's see. Actually, I don't know if I want to do this in X. Yeah, I do. Yeah, we're good. And isn't that at a distance of 2? What about when it gets to D? Because effectively, isn't everything that I just did here kind of A? This is initial, right? This is kind of the A. Now I move over here and say, okay, cool. What's going on over here at D when it gets up to D? What's its velocity when it gets up there? Remember, this is really, and I'll write this in here, in X. Like those are the velocity in what I'm calling X here, right?
or not zero?
It is 0
Oh, yeah.
because when it gets to the top, it's not moving up or down, is it? So actually at that D location, this actually is 0.
It's like our Y, yeah.
And then my force hasn't changed. Force is still gravity, so it's 0.5 times 9.81. But the distance is the one thing I don't know. Like how high off the ground is that? Does that make sense?
Can we assume it's 2 plus the portion of X?
Yeah, it's basically going to be 2 plus a little bit. So I like this equation because it's only got one unknown. So if I type all that other junk on the left side, and notice that velocity is squared, I look down there at 6 sine of 30, and it's easy to kind of forget that that's down there, but so see the left side, I got some big number. On the right side, I just need to divide by 0.5 and divide by 9.81. And I've got the distances. Seems too high. I'm going to write down what I got and then just going to check my work. Based on the picture, that seems like it doubled in height and that doesn't look right. Do you agree with that? So this is what I'm always talking about sense making. I'm looking at that thinking it's not right. Now I'm looking back at what I typed in. When I typed right there, right here, I typed a plus sign, not a multiplication sign. So stupid mistake. So I'm going to go back up, re-hit that, change that to a multiplication sign. Got something even worse. I got 12. Oh, I'm not finished. Then divide by 0.5, then divide by 9.81. I got 2.458. But that's not what 2 of you got. So again, that makes me worried.
So 2.4587.
That's what I got.
I got as well. I got 2.45.
I don't see that I typed anything wrong in. Recheck. I basically got an answer for this side. And then I divided by 0.5. And then I divided by 9.81. Make sure you squared 6 sine of 30. It's easy to forget that squared up there, like I said.
Yeah, I didn't do
Okay, there we go.
Incidentally, I mean, that's, you know, replacing v of x with 6 sine of 30, it would have been way smarter for me to, and you, to like put the square down there, you know, just so you don't forget it. Okay, so that looks reasonable, doesn't it? So another half a meter above that, so it got to D. Okay, great. And so, okay, well, let's just keep going then. Let's go. Let's go work in energy, except for this time, let's go D all the way down to B. Let's go let it hit. We need to go hit down there. Notice last time it was easy because the one that was doing the hitting was just cruising along a straight line. Whereas this one's, you know, flying through the air. So it's like I got to work a little harder to sort of figure out how it's behaving, right?
So with D, we don't care.
So again, I don't care about what's happening in, I don't care about what's happening in the Y direction.
Where is the,
I'm sorry.
where's the,
Okay, I'll show you.
It's like
It's here because I covered it up. It's basically impact. It's at impact. B is the impact spot. It's where it hits the ground.
where's D?
D.
D.
It's like
D
where it
is
starts at 0.
D is the peak up there. I just decided to kind of figure out what did it take to get it there. And some of that was just to kind of do something we did a while ago, just because it's kind of cool to see that in action. Do you agree that was just one equation that answered that? Remember how complicated that set of position, velocity, and acceleration questions were to get it there? That's really cool that I kind of know all that. So it actually has no velocity in X now at this location. So since this is from D to B, do you agree that this speed is actually nothing? At D, up there at the top, we just said a second ago that it's got no speed up there. So that's good. That all went away, and that's because it has no kinetic energy. It's all potential. And we know its force, and its force is 0.5 times 9.81. Its distance we just calculated a second ago is 2.459. So then what's happening on the other side? Do you agree that on the other side, its distance is actually 0 because it hit the ground? So that's cool. And I know the mass, it hasn't changed, 0.5 times 9.81. So then that's going to give me the velocity of X when it lands. And I could, go in here and say this is at B and this is at D. So again, hey, cool, I like that algebra equation. It's not two equations, two unknowns. It's just one algebra equation. There's only one thing I don't know, the velocity when it lands. That'd be really cool to know that. So if I punch all that in, which I'm going to do, I'm kind of looking at my notes from a previous class, and I kind of don't trust what I'm looking at. So 5 times 9.81 times 2.459, all those multiplied. And then I got only one thing on the other side. So I'm going to multiply 1/2 away, multiply by 2. I'm going to divide by 0.5, divide by 9.81. Times 2 divided by 0.5 divided by 9.1.
Oh, but it gets taken out. Oh, yeah. It's taking the forces away.
Yeah, that's.
I'm not confident of it, but I got 2. Your answers sound better than mine. I like that we all got different answers. I think it's funny. So let's see. I typed on the left side, I typed 0.5 times 9.81. I'm just looking back to see what I typed. 0.5 times 9.1 times 2.459. That's right. Then I multiplied both sides by 2 to get rid of the 1/2. Then I divided both sides by 0.5. Then I divided by 9.81. I got 4.9. Took the square root. I don't see that I typed anything in wrong, but my answer just doesn't seem right to me.
Well, your mass should just be 0.5.
Aha! Saved.
There's no acceleration.
There's no, did we do that wrong any other places?
Oh, and B.
Yeah, remember I was doing it with force up here. So where force is the case, it belongs, but I should have just been 0.5, right?
Yeah.
Good catch. Again, sense making. Did I do that on purpose to teach you something? No, just did it wrong because I'm a human. So try that again, times 2. I got 48, take the square root of 48, 6.946. Does that agree with anybody now?
Yeah, I got that.
Meters per second, not feet per second. Thank you.
If I should 0.5 on the other side, it eliminates the 0.5.
Well, should that one
Which one?
should the 1/2 on the left side?
It's multiplied by 0.
Yeah.
So then
Like you multiply both sides by two.
you have to get rid of the 1/2 on the right side. But the one on the left side is already gone because it's multiplied by 0, so it's being applied to the force one direction.
Now, let's make this calculation. If I go back to the original when it was 6 up there, do you agree if I took 6 and multiplied by the cosine of 30? 6 cosine of 30, what time is it? It's about time to get out of here. 5.196. What does that number represent?
Velocity in the y direction, so it's your final velocity in the y direction.
Yeah. So that doesn't change, right? That's still the velocity in the y direction. It's the velocity in the y direction the whole time. Again, assuming the ball skidded off of the floor in such a fashion that it didn't lose anything. Is that realistic? Not really. But whatever. They said, I think they said, did they tell us that? Did they say? Did they just expect it to assume? Yeah, they expected it to assume this time. They didn't say anything about that, which is fine. So I'm just going to make a note here and say this is both initial and final. But what is this one?
Well, it all depends on.
That's only a.
This is actually initial. Do you understand that? This is like right as it hits the ground. But then it's going to bounce off the ground and it's going to get less.
So wouldn't our initial be on D?
Yeah, because this is at B. That's where we are here. We're at B now. But we haven't bounced away from B. So this is like a billionth of a second before B.
It's like kind of in the overall picture of it.
But we found it at, so, but we're just saying that it's just before it.
Yeah, that's right. So that's why I just wrote initial there because it's actually just before impact. But now it's about to bounce off and a billionth of a second later, it's going to be slower thanks to that 80% reduction, right?
Mhm. Okay.
Okay, well then let's go try to get that. So E, we were told was 0.8. And we said, oh my gosh, velocity.
VX minus VAF.
It was
VBX
final over initial, right?
Yes. A VA final.
Yeah, so in this case, I don't ever really need the B's and A's. Yes, I do. I do need those.
VX final minus VAX final.
And then it just got reversed
And they're all initials.
and they're all initials. Is that true? Now let's just make a note to ourselves here because this is kind of confusing. This worked where A was the ball, where B is the wall in this case. Does that make sense? The one that did the hitting here was the A ball before, and the one that got hit was the B ball. Well, here the A ball is the ball, but the B ball is a wall, right? So what's the wall doing this whole time?
Standing still.
It's not moving. You agree with that? So the wall never went anywhere. Wasn't moving later, never moved. Notice in this case, that 80% is literally just the percent, like because that other one didn't move. So I do have my initial, and that's why I took the time to write that in. I do have that this initial speed right here was 6.946. So this is just a straight percent. So if I take that 6.946 and say times 80%, so when they're both moving, it's not quite that simple. You can't just take 80% of it and you're done. But when one of them isn't moving like a wall, you actually can. 0.8 times 6.946.
Yeah, but it's the velocity right before the impact. would assume of taking the velocity on B and then done the 80%.
So something was lost. Maybe I'll go back and throw a little O in there. Yeah, let's see. Is this, what about negatives? I just heard somebody say negatives. I wasn't thinking about negatives. Does that matter?
Well, your velocity is going down. So your initial velocity should be negative.
Yeah, it's like our initial velocity back here should be negative, right? Could it be negative? Notice it's being squared and therefore it could have been negative, couldn't it? Isn't that interesting? You know, if you have the picture, does it matter that much? Not really. I mean, the picture is kind of okay, but I think that's exactly right. Technically.
Just check your equation positive if you're throwing negative.
So I'll go back and throw that negative in, but it did bounce up. And so, okay, that makes sense. And so again, this is all X because we already know what's happening with Y. Now, what do I do to sort of figure out how high in the air it's going to go? Remember, I don't really care. They didn't say they cared where that is over there. It's just kind of how high is it? So I can literally think of this as like a ball that hit the ground and bounced up. Does that make sense? Again, working energy equations is probably the easiest way to do it.
Oh, so that's what I'm going to find from B to C.
So now let's go from B to C. So we're going from B to C. What's happening at B? Well, I've got a mass. I've got a velocity that we started with. That was 5.557 that we just calculated. I have no distance because I'm on the ground. You agree with that? So I've only got kinetic, motional energy to start with. I have no potential. Now, what am I going to do when I turn this around? I'm going to have no kinetic energy because it reached the top. So it's not moving at all, right? At C, it's not moving at all. It's all potential. Force is mass. I do need that acceleration. And I like this equation because it's only got D. It's only got one unknown. I never had two equations, two unknowns this time. Notice the masses actually cancel out there. That's just kind of fun. In the end, if you drop something, it doesn't matter what size it is, it falls at the same rate, Newton. So in the end, I'm really taking 5.57 squared. I was about to forget the squared, and then dividing by 9.8. 5.557 squared, 30 divided by 9.81, 3.147.
No, because you forgot the half.
Forgot the half. Yep, good job. So I got that 30 times a half, then divide by 9.81. I got 1.57.
Yep.
So, you know, again, does that feel pretty powerful to think, wow, just based on work and energy equations? Notice I never had to come up with angles. I was kind of thinking when I first did this, oh man, I'm gonna have to figure out what angle it hits the ground at, right? Like, oh, that's gonna be hard. I'm gonna have to find an equation, take its derivative, figure out how many degrees. But thanks to work and energy, I didn't have to do any of that. Thanks to the fact that I knew that, you know, what we're calling here vertical is the only thing that was changing. Then I didn't have to make any of those calculations. That made my life way easier. So I only concern myself with the line of impact direction. I didn't really need the y at all. The fact that I calculated it, did you notice I never even needed that? Like I thought I was going to need it, but I never needed it. Isn't that interesting? Never even used it. Not necessary, oddly. But it's pretty, again, it's pretty cool that I have that much predictive power. So the two simple problems are, ball runs into ball smacks off of wall. Can I just kind of figure out what's going on, where it's going to go? As a side note, notice it's not 80% as high as it used to be. Or is it? If I take, I need to shut up here, but if I take 80% of that height right there, I wonder, I'm just curious, 0.8 times 2.459. We got 1.96, like it isn't 80% of the height. It's 80% of the velocity. You see what I'm saying? Now, only do this if you want to, but did I actually need to do for extra credit? Could I have just went straight from A to B? I actually don't know the answer to that. Just go A straight to B. Did I have to stop off up there at that top? Did I need to do that, or could I just gone straight A to B? Wasted my time. My gut reaction is, yeah, that's true. I'd have to calculate the fact that my initial velocity was positive because it was going up, right? And it seems like I did not need to do that in terms of just answering this question and, being done. That's both interesting and not very hard. This is a good extra credit to do. Probably teach you something. All right, let's shut up and take a break.